Welcome. In continuation to our earlier lectures on the refrigeration and liquefaction systems which are relevant to the processing of the natural gas, here we learn something more. So, in this particular lecture, we shall be learning about some other techniques for liquefaction and refrigeration. That is, one is Linde dual pressure liquefaction system, then cascade system and Claude refrigeration system. Now, first let us come to the Linde dual pressure liquefaction system. Now, let us see what is the motivation of the dual pressure of liquefaction. The motivation is this, that it has been found that in the Linde liquefaction system, that whatever the amount of the gas is being compressed, only a small fraction of that gas is liquefied. So, naturally we are investing quite an amount of work for the compression of the total gas without able to get as much amount of liquid from the gas. So, what's happening that it's found that the work of compression is proportional to the logarithm of the pressure ratio. For example, you might have remembered that if it is the ideal gas, then the work of compression comes to RT into log of the compression ratio. So, that is how we see that the work of compression is proportional to about the log of the compression ratio. On the other hand, liquefaction varies almost linearly with the this compression ratio. So, what we find that if we can reduce this compression ratio, then we shall be able to reduce the work requirement, but at the same time the liquefaction will also be reduced. Now, it has to be seen whether the reduction in the work requirement can offset the reduction in the liquefaction. If that is so, then this kind of system is workable. So, in this view of this, it is suggested that a fraction of the gas, not the whole of the gas, but a fraction of the gas is compressed to some intermediate pressure and then further compress the whole mass of the gas to the actual pressure. Then and this way what happens that it reduces both the energy requirement for work of compression as well as the liquid yield for a given cooling due to reduction in the compression ratio. Now, it has been found that the reduction in the work requirement is much more than the reduction in the liquid yield, and but what happens, the disadvantage is this, that even though we are able to reduce the work requirement without sacrificing much of the liquid yield, but it increases the process complexity, and that is how the controllability of the process it becomes all very difficult. Now, here is a typical Linde dual pressure liquefaction system. Now, as you can see here, there are two compressors, and this is the first compressor and second compressor. Now, what we find here is this particular compressor is getting some amount of the gas, that is m dot, and this gas is compressed to some intermediate pressure in the state 2, and then this gas is joined by the return stream from first evaporator. This is coming here, and then what happens is together the total gas is now going to the second compressor, and it is going to this 3-channel heat exchanger where it is being cooled by the return vapor streams from the 2 evaporators, and then it is going to the JT valve where it is getting expanded and two phases are being formed. The liquid is stored here, whereas the gas is this vapor is sent back through this 3-channel heat exchanger back to this, and it is joining here. Okay. So, this particular liquid, now what is happening, this is again taken to the second JT, and here again it is getting into two phase, and from here this liquid is a final liquid reservoir, and from here we are getting the whatever liquid we want, and this vapor is going back through this 3-channel heat exchanger and it is going to this the inlet of this particular first compressor. So, we find that we need two liquid receivers. So, and from these two receivers we are getting some amount of this total gas, And here we find the first from the one whatever you get in the first one, that is about mi dot. This I signifies intermediate, and this particular thing is m minus mf minus m dot. This m is the total mass, this mf is the amount of the liquid withdrawn from this reservoir, and mi is the amount of the gas it is coming through this particular reservoir. So, this is simply obtained from the material balance, okay, and that is how we are able to get the total amount here. Now, here we find that by doing so we are having the two work done on these two particular compressors, and we have to supply the makeup gas so that we can compensate for the lost liquid from here. So, this is the overall Linde dual pressure column, and this can be represented on a TS diagram like this, that we start with some initial pressure at 1, and then we isothermally compress it to some intermediate pressure to 2.2, and then it is ultimately going to the final pressure to 3. Now, here please understand that here we are not showing the various types of streams, the amounts we are not showing in this TS diagram. It is just that any TS diagram or any kind of phase diagram just show the states of the various equipment. So, here from the now what we are finding that from 3 we are now cooling it down isobarically, and then we are going to the first one. So, there is a first evaporator. Now, here what we are doing, that we are getting the liquid and the vapor, and ideally we assume that both the liquid and the vapor are at their saturated conditions. Now, the vapor stream is sent back through the 3-channel heat exchanger, and here we are again it is getting heated up at the intermediate pressure, and the liquid is again partially evaporated to another this initial pressure, that is P1, and we find here that we are getting the liquid. This liquid is part of this liquid is withdrawn, and the vapor is taken, and it is isobarically heated up to the inlet pressure of the first compressor. So, this is how this is the first compressor. So, this is the second compressor, and that is how we are getting this dual pressure operation and on the TS diagram. And if we do a first law analysis, what we find that this will be the yield of this particular system. Now, here we find that this I is signifying the intermediate pressure stream flow ratio, which is given by this mi dot by m dot. Now, here we find this for first term on the right hand side is the liquid yield as obtained in the simple Linde system, whereas this particular term is signifying the reduction in the liquid yield due to the dual pressure, but this reduction is not so much as a reduction in the work of compression. Now, here we see the work requirement given for the dual pressure system, and here we see that this first term is the same for the Linde system, and this particular term represents the reduction in the work requirement, and generally it has been found that optimum value of I is about 0.7 to 0.8, and the work requirement per unit mass of liquid produced is found to be less than that for the simple Linde system. So, that is how this Linde dual pressure liquefaction system proves to be better than the simple Linde liquefaction system. Next, we go to a cascade system. In fact, cascade system is the one which came into the technological advancement for the first time before the Linde, and this was basically to liquefy the air. So, here we are taking it later on, so that we, after learning the pre-cooled systems, we can appreciate this particular cascade system. So, this is an extension of the pre-cooled system, and the pre-cooling is done to the pre-cooled systems too. That means, whatever we have found earlier that we were doing only one pre-cooling to the actual system. Now, in this cascade system, cascade means there is a series of systems, and this series is coming due to the use of the pre-cooling for the pre-coolant again. So, here we can see that there is a cascade of the various refrigerations, and here is the actual system. Here we are getting the liquefaction, and for this particular liquefaction system we are using this particular precoolant. Okay, and this for this particular precoolant circuit again we are using another precoolant circuit here, and again for this precoolant circuit we are using another precoolant circuit. So we see that the precoolant circuit, that there is a series of precoolant systems for the this kind of cascade systems, and here for example we have shown for the liquid nitrogen production that we are using ammonia, then ethylene, then methane. Now if you see that these precoolants have been arranged in the decreasing order of their boiling points. Okay, and ultimately we find that for the ammonia we are using the cooling water as the heat sink. Okay, so this is how we are carrying out the cascade system, and here the typical values have been given that ammonia is to liquefy ethylene at about 19 atmosphere, the ethylene is to liquefy the methane at 25 atmosphere, and methane is to liquefy the air at about 18.6 atmosphere. And this particular system came into being as early as 1933, and this way whenever we are using so many precoolants, even the more the number of precoolant systems, what we find, this will be moving towards a reversible system. Why? Because we shall be expanding the gas at a smaller pressure ratio, and we know from thermodynamics, if the pressure ratio is small, the system becomes more and more reversible. And but the disadvantage is this, that because we are having so many subsystems rather, then it becomes difficult to maintain, and in kind of cryogenic systems if there is any kind of heat inleak or the material inleak, that becomes problematic, and some material may be posing some kind of safety hazard to the personnel or the environment. So this kind of cascade system becomes a bit difficult to operate. However, in case of LNG, such cascade system, that is to produce the liquefied natural gas, such kind of cascade systems are being used. Now next we come to another very important system, that is the Claude refrigeration system, and this system approaches reversible refrigeration by an expansion engine done isentropically. Now this, as we learnt earlier, that there are two ways of expanding, either by the internal work that is done in the expansion valves or the external work that is done in the expansion engine. So in this way we find that the expansion engine we are using, and Claude was the one who first used the expansion engine, and expansion engine can give better cooling and more reversibility than the expansion valve. So we find that expansion engine gives a lower temperature, and in this case what we find that the gas is first compressed to about 40 atmosphere. That means in this particular compressor from 1 to 2 the gas is compressed to about 40 atmosphere, and then it is taken to a cooler, and from the first cooler, main cooler, a portion is diverted, and this portion about 60 to 80% is diverted and passed to an expander. And after the expansion the gas becomes quite cool, and this is taken back to the inlet of the return stream to the second heat exchanger. So that means this portion is mainly to cool down the rest of the incoming hot gas. Now after this the things are pretty simple, that this gas is taken to the another heat exchanger for further cooling before it is taken to the expansion valve, and here the Joule-Thomson expansion happens, so that we are getting the liquid here. This is the evaporator, and this evaporator is taking the heat load from the refrigerated space, and it is getting vaporized. That means it may be assumed to be an isothermal source of heat, and then the vapor stream going back through these heat exchangers, and here after this heat exchanger it is getting joined by this particular cold stream, and slowly it is going back to the inlet of the compressor, and that is how this particular system is going on. And here we find that a part of this particular thing is mg, and me is the amount which is being diverted from the mainstream through the expansion engine. Okay. So, on this particular system, we are getting only m dot minus me dot amount of the fluid. Now, going further into this system, first we look at the TS diagram for this system. Here we find that the gas is first getting compressed isothermally from state 1 to state 2, and then it is isobarically getting cooled down from this is the first heat exchanger. After that, a stream is being diverted to the expansion engine, and ideally it is undergoing an isentropic expansion, and this particular dashed curve is showing that if it is not isentropic, it is simply maybe adiabatic but not reversible, then we find that it is taking another path, and in this path we find that the entropy is more, as we know that the irreversible processes will have more entropy. So, we find that this is taking going the right hand side of the isentropic line, and the rest of the gas is going further in a stage wise manner to the other two heat exchangers, and then we are finding that it is going to state 5, and then from here we are isenthalpically expanding it through the expansion valve. The liquid is coming on the saturated liquid line, and this liquid is taken out, and the vapor is going to the saturated vapor line, and it is again getting isobarically heated, and here it is being joined by that stream which is coming from the expansion engine, and then these are getting further heated up isobarically, and through the various heat exchangers, these 7, 8, 9, they are all signifying the heat exchangers, and then ultimately they are reaching the point 1, that is the inlet of the compressor. Now, if we do a first law thermodynamic analysis on this system comprising heat exchangers, the expansion valve, the evaporator, and we assume that the kinetic energy and the potential energies are not changing appreciably, and we are neglecting any kind of heat inlet to the system, then we find this is the amount of heat absorbed by the refrigerant in the liquid reservoir, and here we find this H1 prime is coming, this is the actual enthalpy which is there, and this is the isentropic this He prime shows the actual entropy which is of the coming at the outlet of the expansion engine if the expansion is not isentropic, and if we take this as the expander adiabatic efficiency, and this X is the expander mass flow ratio, and we put this expander mass flow ratio as the ratio of the amount which is diverted to the total amount of the gas, and then we can find this is the work requirement, and in this work requirement we are finding that these are the various efficiencies. This is the overall efficiency of the compressor, and this is the mechanical efficiency of the expander, and this is the adiabatic efficiency of the expander, and now we are finding that these are ideal values we are putting here as S1, H1 and He. So, they are ideal values. So, this is how we are able to find out the net work requirement for the gas compressed. Here please understand that this particular portion shows that this work is the work which is being produced by the expander. Now, in case we are integrating the compressor and the expander, only then this particular term will come. That means the actual work requirement for the compression will get reduced. However, if we are not integrating the expander with the compressor, then this term will be absent. Then it means that the work requirement will be same as in case of the simple Linde-Hampson. So, this is how that is how we should be integrating the expansion engines to reduce the work requirement of the compressor from the external source. Now, moving on to the Claude liquefaction system, here we find the system remains almost the same except that we are having a liquid withdrawal from the reservoir, and this is not an evaporator, this is a reservoir, and here whatever amount we are withdrawing, that amount has to be compensated for, and that is being done by the makeup gas. So, this MF is coming out, and this MF is again given as a makeup gas, so that the total amount of the fluid inside the system remains the same. So, here we find the same 3 heat exchangers are there, and here from the first after the first heat exchanger we are diverting a stream to the expansion engine, and the outlet of this expansion engine is going to the inlet of the return stream to the second heat exchanger, and rest of the processes are the same as in case of the Claude refrigeration. So, because it is liquefaction, so we need to know what is the liquid yield, and if we apply the first law of thermodynamics to the combined heat exchanger, expansion valve and the liquid receiver, we get this particular expression. Now, in this expression what we find that the first term on the right hand side is the same as the one we obtained for the simple Linde-Hampson cycle, and this particular term is showing the enhanced liquid yield due to the Claude liquefaction. So, that is how we are finding that Claude liquefaction gives us a better liquid yield than the simple Linde-Hampson. And these are some of the other variants of the Claude liquefaction system, like Kapitsa system, Heland system, dual pressure Claude system. These I am not going into detail because all these systems are basically developed for the air separation purpose, and as and when we get some special kind of liquefaction or refrigeration system for the natural gas processing, I shall be talking on that under that particular heading. And these are some of the references you can refer to get the details about these types of system. Thank you.